Hi, I'm Saraf from Stanford, and today we're going to talk about the UV LED mission, which was a flight demonstration of charge management using UV LEDs. I'm giving this talk in place of Sasha Buchman, and along with Sasha, Chinyang Lui, J.Lipa, Su and Wang, and of course R.L.Byer. We are collaborating from the Hansen Experimental Physics Lab. Okay, so charging is obviously a big problem in these inertial sensors, and many disturbing forces come in on the spacecraft and go through the spacecraft in many instances. So solar, atmospheric, micrometeoroids, they disturb the spacecraft, and drag-free operation usually takes care of that. But charging is something that happens right in the inner sanctum of the reference sensor, and direct charge particles accumulate on either the proof mass or the housing. When you uncage or separate the test mass from the housing, once you're deploying your sensor, you get a charge imbalance. And of course, we have secondary particles that interact with the spacecraft, the knockoff electrons, which can certainly find their way to the proof mass or the housing. And this potential imbalance, as we all know, leads to an electrostatic force, and it disturbs the inertial sensor. All right, so inertial sensors, they've been around. A few of them actually have launched successfully, starting with Discos on the Triad 1, pioneered by our colleague Dan DeBray. His picture is out there. And they did their discharge by just essentially shorting the test mass to the housing. It was launched way back in '72. Gravity Probe B, they used a mercury lamp running at 254 nanometers. And I think they had fairly good luck with charge management. And then our mission with KACST and Ames, we are using LEDs for the first time at 255 nanometers. We launched in June of 2014, and I'll talk about the mission results. And right on our heels, the Pathfinder went out, but they used the old technology of mercury lamps. And then microscope, testing the equivalence principle, they use a gold wire to essentially to neutralize any charge between the test mass and housing. Okay, so UV LEDs, new technology. LEDs have been around for a long time, but UV LEDs for this kind of applications is new stuff, commercially available, went through an excruciating space qualification process by Stanford and Ames, lifetime testing, more than 5 years, radiation testing, shake, bake, and shock. And these devices are essentially aluminum gallium nitride based, 4.86 EV band gap, 255 nanometer line with a 12 nanometer full width half max. You can get more than 10 microwatts from a single device, small, long lifetime, lightweight. We can fiber couple them, and with very low power consumption. We can modulate them so that we can run the charge management outside the science band. And these are just some pictures of some LEDs to give an idea of their size and packaging. And at the bottom, some results before and after thermal and shake and bake done by our graduate student Karthik. And you can see that we didn't see much change after during the space qualification process. All right, so once we had all this done in the lab at Stanford, it was time to send it out into space, and KACST was our space partner out of Saudi Arabia. And of course, Ames was helping us with the launch and all the pre-flight work. Our goal was to measure performance and see if there was any degradation over the lifetime of mission operations, do the electrical and power measurements, and also demonstrate charge management in space. And I'm going to talk a little bit about AC charge management that we did quite successfully. All right, AC charge management, essentially we have a bias plate and the proof mass and LEDs, and we can drive the LEDs in phase with the bias plate or out of phase. Turns out if you do it in phase, you're going to pull electrons from the proof mass onto the bias plate with the bias plate at a positive potential. You pull out electrons, the proof mass potential rises, and you can reverse this process by driving the proof mass negative and with a negative bias plate, and you can essentially go up or down as needed. So this is the experimental setup in our lab at Stanford. Karthik set it all up. It's a single LED with a bias plate, and he used a non-contact probe to measure the potential of the ball, of the proof mass. Ultim, high resistance spacers were used to kind of support the ball. And here you can see that with the function generator, he's modulating the bias plate and the current source in phase or out of phase, as I talked earlier. And with an electrometer, he's measuring the potential of the ball. So this is a picture of the ball inside the housing, and this is the thermovac chamber testing that we were doing at Ames in Mountain View, California. All right, so payload. Now that we got it all done on the ground, time to put it in space. Some rough dimensions of our payload. It's an 89 millimeter gold-coated sphere, and we had two identical experiments running. Experiment number 1 used a particular package, TO95 type package for the LEDs, and on the right there's a different package. They're directly SMT'd onto these little circuit boards. There were 4 bias plates, 1, 2, 3, and the 4th has been taken out. And there was a contact probe, and there was a circuit board on the top and the bottom for again redundancy purposes. Launched it on June 19th aboard a DNEPR rocket from Kazakhstan. Mission operations were designed to be identical to ground testing, and we wanted to again study the power curves, degradation, lifetime testing, characterize passive and AC charge management, and of course also look for temperature dependence of the UV LED parameters on temperature. Okay, so quick results. You can see the VI curves for experiment 1, experiment 2. You can see the band gap is roughly about 5 volt-ish. All LEDs did well. They matched what we measured on the ground, both for VI and output power. And this output power we are showing is a measurement from the built-in photodetectors. And when you convert that to effective power, we're talking about 100 microwatt-ish type levels of optical power. Examples of UV LED data runs. The bias potential, we raised it and lowered it and raised it and lowered it, and the test mass followed suit. And similarly, we changed the duty cycle from 10% all the way to 90% to show that we could, affect charge management rapidly at higher duty cycles. And we did a number of other experiments, and I don't have time to go into that. We did passive charge management. We took the ball, raised its potential with the UV LEDs to about a couple of volts, and then we turned off the bias plate, sent it to 0 volts, and then turn on the LEDs and essentially characterize the charge on the ball for different LED currents. So you can see this is about a milliamp flowing. It takes a bit of time to get down to 0 potential, and 9 milliamps. You can see it's almost within 2 seconds we go from 2 volts to 0 volts. So what does all this mean? Well, LISA requires about 1/10 of a picocoulomb discharge, and the quantum efficiency that we measured in the lab for a gold-coated sphere was 5 times 10⁻⁷, and for 1/10 of a picoamp. It turns out if you do the calculation based on the quantum efficiency, power, and the wavelength, it takes us about a second to discharge the sphere. And similarly, we calculated the photocurrent at 10 milliamps. Same calculation comes to 27 picoamps, and when you back out the photocurrent based on the discharge curves, we get about 28 picoamps. So we are doing quite well theoretically and practically. Looked at the zero scattering before and after, and you can see that we had about a 2 millivolt zero scattering RMS differential, which corresponds to about 0.06 picocoulomb for about a 28 puff test mass capacitance. Okay, won't go into these details. You can imagine a situation where we have a sandwiched single UV LED inside the housing. Turn it on for a few seconds every 4 hours, and you are affecting charge management quite effectively for the requirements of LISA. About 100 electrons per second every 4 hours. 1/10 of a picocoulomb can be discharged quite easily. So the outlook, UV LEDs are a robust and compact source of photoelectrons, and we have demonstrated that with this mission. No charge measurement required. Precise timing, Power stability, the determination of the illuminated surface, this is not that necessary, or precision is required in the maintenance of these surfaces. Fiber coupled LED conveniently delivers photons to where they're needed, and the technology is at TRL9 level. Questions, and we have a paper out in CQG from 2016. You're welcome to look at it for all the details, and I'll be happy to answer questions when our session arrives online. Thank you for your attention.